Hi everyone, let's go ahead and get started with what is transformers, and then we will be using this transformer dataset to recognize the emotions on a Twitter dataset. So the transformer you can use as these 4-step process. So you have your dataset. After this dataset, tokenization will happen to your dataset, and then you can use your transformer model. Thereafter you will be using their test dataset to evaluate your model. So there are many transformers which have came in last few years, like we have the first transformers around 2017. Thereafter this transformer was built based on attention network, and thereafter ULM fit came, and then the GPT-BERT, GPT-2, Robert, DistilBERT, XLM, DBERT, GPT-3, T5, all these came, and recently GPT 3.5 and GPT 4 has also came, which is very widely being used in our community nowadays. So these networks are based on the transformers. These are just a few networks. There are like hundreds of the transformer models available on HuggingFace library. So the HuggingFace library or HuggingFace hub is a place where all these models are hosted there. So you can see that HuggingFace here. I'll show you in a while from where you can download your data itself. Now you see there the transformer architecture here. It has these type of the architecture in the transformer. We have tokenized text data, as I had told you here that you need to do tokenization before putting into the transformer. But once you download your transformer from the HuggingFace or Hugging Hub, from there you would be seeing there these tokenization will happen there internally with the transformers. So here it has the tokenization. So once this tokenization is done, so the tokenization is like breaking down the strings into individual tokens. Thereafter token encoding will happen. This you can treat as one hot encoding, and then these one hot encoding will get converted into a token embeddings. And along with that, a position embedding is also mixed with the token embedding. It is required because the positions of these tokens also matter into a sentence. Once all these things goes, then a final hidden states are created. So these final hidden states are known as a vector representation. In a BERT, we have 768 dimension vectors. There you have an encoder stack. So you can say the transformer works as the encoder and the decoder stacks there. So first encoder is there, and thereafter decoder is used here. So this encoder and these decoder have here multi-headed attention network. So multi-headed attention networks are a neural network which actually focuses on most important tokens on a given sentence or on given paragraph there. Once this encoder produces their key and value feature, or you can say they are the embedding, then these embeddings also goes to the decoder stacks there. And here now you see there is again a different output is coming there. So this is used for the training purpose. Alright, so this is used for the training purpose only. So what you do generally, you pass one input here at the encoder and a right shifted input to the decoder as well. So once these things goes, and then the final predictions are made here. Based on that, this whole neural network works together. This whole transformer works together. Now here is a trick. So generally we do not use this whole transformer as the network. Sometimes we use this encoder as the network. Sometimes we use these decoder as the network. So here are the some of the application where we use these transformers. We use these transformers in various tasks of the natural language processing, like the translation of the text data, text summarization, question answer, and sentiment classification, named entity recognition, and so many more things. We can use these. Now, once you are working with text classification task, then you just need to use these encoder part from the transformer. You do not need to use this whole thing. If you are working with the translation work, then you can use this either whole transformer, or you can just use this decoder network as it is. So this decoder network also can work as the sentence, the translation here. Alright, so these are the process which we just discussed here. Each of these processes are described here, and this notebook is given on my GitHub account. You can take this notebook from there itself, and then you can practice this by yourself. So we'll be using here a text classification architecture from our architecture. So that architecture, you can see it here. We are taking here only encoder for our text classification. So our data will be given, a tokenization will happen, thereafter tokenization encoding will happen, then the embedding will be generated, and then the encoder stack will be placed there, and thereafter hidden states, and then finally these orange color which you see there, this is a deep neural network, or you can say the fully connected networks, or you can also say that a classification head. So these part we will be adding into our transformer encoder, and then finally we will be retraining our model to get the prediction. We will be using here emotion dataset from the HuggingFace. I was telling you that this HuggingFace here itself, I'm just gonna click on this HuggingFace and let me zoom in. Now this is HuggingFace. So here we have emotion data in HuggingFace. So this emotion data can be used as the text classification. This is multi-class classification. Its language is English, and this is monolingual. That's mean there is just English language. And thereafter, now you see there, you have here text data. I didn't feel humiliated. This label have here a sadness. I can go from feeling so hopeless to do some damned hopeful just from being around someone who cares and is awake. This is also zero and sadness. There is the anger, love. So these are labels here which we will be using. So there are 6 different type of the labels here which we can use for our classification. So we'll be downloading this dataset directly in our notebook from the HuggingFace dataset, and then this emotion dataset will be having a text column and the label column. So this text column will be tokenized, and thereafter encoding will happen, and then embedding will be generated for these text data. Once embedding is generated for these text data, then these embeddings will be a contextful embedding. That's when these text embeddings will be so meaningful that we can do the classification with the very high accuracy. Alright, now let's go ahead and get started with the coding part here. So these are some necessary libraries which we will be needing for our text classification. Alright, so we are going to do here emotion classification. So these I'm gonna just uncomment these, and then I'm going to install these libraries. So this will take a little time to install all these library on your notebook. Your notebook will first connect to a virtual machine provided by Google Colab. Once it is connected, then it will install all these necessary libraries there. So installation is done here. I'm just gonna delete this output from here. Now let me show you our dataset, HuggingFace dataset. Here it is. You need to just click on here. It will lead you to the dataset. So this dataset has here a 3 split: train, validation, and test split. Train split have 16,000 rows, validation split have 2,000, and test split also have 2,000 rows. You can see here by selecting here validation, you can see validation split dataset. Similarly, you can select here test split just to see the test split dataset. Alright, so we will be using here a datasets library. As you see here, we have installed datasets. So we'll be using this package to download our emotion dataset from HuggingFace Hub. Let's go ahead import pandas, and then we are also going to see that how many total datasets are available at HuggingFace, just to understand for a general idea. So I write here import pandas as pd, and then from datasets import list datasets. Alright, so this list dataset is going to give us all the dataset available at HuggingFace. You can simply write here all datasets is equal to list datasets. Now you print this all dataset, do remember it is not downloading dataset, but in fact it is just downloading the name of these dataset. And if you just print this all dataset, you will see here all these datasets are there at HuggingFace Hub. You can check the length of these dataset. You will get like 20 to 30,000 datasets, probably more. Let me see here. All right. So it's a 50,000 dataset. Around 2 days back, I checked the total length of the dataset. It was at that time 48,000, and now it has reached to 50,000. So seems like in last couple of days, around 2,000 dataset is uploaded at HuggingFace Hub. All right. Let's go ahead and download our dataset, emotion dataset. We will be needing this emotion dataset for our classification task. Let's go ahead and first check if emotion dataset is available here in all dataset. So what you can write here, you can simply write here emotion in all datasets. So it says that it is false. The reason is here, you see there these emotions are here at this particular location. So you will find here this particular the address you need to give here just to make sure that you find this emotion. So it says that here true. So by default, if we pass just emotion data, it will take from here itself. So what I'm going to write here, from datasets import load dataset, and then I write here emotion equal to load dataset, and in that I'm just gonna give here name of our dataset, which is emotion. Now if you run this, you will see that this data will be downloaded here on your local PC or on Google Colab, whatever you are using. So it download these data in chunks. Now you can see all the chunks are downloaded here. And if you print here this emotion data, you will be seeing here all the split which we had seen previously, like train split, validation split, and test split. Train split have 16,000 data, validation have 2,000, and test split have 2,000. Let's go ahead and set the format of this dataset dictionary as pandas data frame. You can simply do like here, set underscore format type is equal to pandas. So with this, we have set here our dataset format as the pandas dataset. Now if you print this emotion, you will see we were seeing earlier, but if you get it here, this train sample, now you would be able to see this data as pandas data frame. Alright, so this is now a data set. You need to select all rows and the column if you want to see it as the data frame. Now you can clearly see this. If you do not run this particular thing, so you would not be able to see this as the pandas data frame. So this you have to make sure that you set a format as pandas data frame here. So there we have our train data. I'm gonna give here data frame df is equal to train data, and then I write here df dot head. Now you see their labels are given here in integer format, but if we see it at HuggingFace, these labels are given in integer format along with the class labels are also given there. So how would you get these class labels from the dataset? It's very easy process to get the class labels. We are going to get here emotion.train, and then if you run this, you will see here two keys of this dataset dictionary, features and the number of rows. So basically I'm just gonna do here train.features. Now inside this features, you will see here text data, which is here, and then the label data. So this label data have here the class labels, names are here. So the features, and inside that I'm gonna put here label dot names. Now if you run this, you will see here a list here. So this is the classes. So there are 6 classes. These 6 emotions we are going to identify from the given Twitter data. You have sadness, joy, love, anger, fear, and surprise. And this 0 represent here, this is sadness, 0, 1, 2 and 3 is anger here, and 2 love is here, and 3 anger is again here. So we have got our class names. Let's go ahead, add here label name as well. So that is very simple process. I'm gonna use here df label name equal to df label. So I'm gonna use here lambda function. So I'll be using here apply and then lambda x, and then I need to call here these classes. In fact, I need to get the index value using these values. So I write here x. Now you would be able to get this df. If you print the head of the df, you will be seeing their label and the label name as well. So we have sadness, anger, love, anger. Alright, now we have our data frame. Perfect. Let's go ahead and get started with data analysis. So the first question comes, why do we need dataset analysis? We need dataset analysis to understand more about our dataset, our class distribution, and overall data distribution. Let's go ahead and import matplotlib pyplot. So we are going to write here import matplotlib.pyplot as plt. Thereafter, our data, train data, we have in data frame, and here we have label name. Let's go ahead and get the label name count. So with this, you will understand that what is the count for each of these labels. We have 5,362 labels for joy emotion, 4,666 labels for sadness, 2,159 for anger, and then 1,937 for fear, and then love, and then we have here surprise. If you want to see it in a bar plot, you can simply use these label count. So I'm just gonna give here like this label count, something like this. Then you can simply do on this label counts. On this you can do a plot, because this one is what you see here. This one is actually a pandas series. So on this pandas series you can simply do here bar plot, something like this. If you run it, you would be able to see here a bar plot. So in this horizontal, this bar h means horizontal bar plot. Otherwise you will see here a vertical bar plot, something like this. Horizontal seems better in this case, so we are going to write here. Thereafter I'm going to write here the plt dot title, and then I write here frequency of classes. Then I write here the plt dot show. So what you have here, surprise have less numbers, and whereas this joy have a very high number. Other than that, if you want these at the top, you can simply put here in your value count as ascending equal to true. So in this case, you will get that the large value at the top. So this says that our dataset is imbalanced dataset. If you use a traditional machine learning algorithm in imbalanced dataset, the performance of model would not be sufficient. But in case of the transformers are very good to work with imbalanced dataset. Although if you want to balance this dataset, you can use imbalance library to balance this dataset. Otherwise, transformer works very well on the imbalanced dataset. Let's go ahead and do a little bit more analysis on this. Thereafter, we will move to the text to token conversion. That's mean toward the transformers. So here we have our data frame again, df. In this data frame, this text data, now I want to understand that what is the word length for each of these tweets here. So for that purpose, if you put here df.text.str.split, and then I'm going to apply here length function. So this one is going to give us the length of each of the tweets here. These are the word length. And this one I'm going to store into a new column. The name of columns are going to be here words per tweet. Something like this. Now once you have your words per tweet, we can simply do a box plot on this itself. So what I'm going to do here, I'm going to do here df dot box plot, and the column which I'm going to select here, words per tweet. This is the column on which we are going to apply our box plot. Thereafter I say here, you need to show this, you need to plot this, you need to plot this using a word per tweet, and along with that we will be also using this by says that there will be a segmentation for our box plot based on these labels. So I write here by label name. If you do like this, you will be seeing here box plot for each of these emotions. So with this, what you would see here? You would see here for love messages or for love tweets, the average number of words per tweet is a little higher than the sad tweet. So these are not very much differentiating features, but just for your understanding and your general understanding, you can see that how these are varying here. The maximum length with this, we see that mostly the maximum lengths are here 50, and the max length we can see here less than 70. So some of these analyses will help us further when we will be using transformers to understand that what should be our maximum token size. As you know that the transformers like the BERT transformer or DistilBERT transformer, these transformers can use max to max 512 tokens only. But a bigger transformers like Big Bird, those transformers use 4096 tokens. But we will be using here a DistilBERT transformer, and most of the transformers are limited with 512 tokens. So these number of tokens falls well below the maximum limit, so there would not be any issue while applying our transformers. Alright, now let's go ahead and see how you can convert your text data into tokens so that we can work with the transformers. Previously we have already seen that the maximum length of the transformer which we are going to use today is 512, and our data have maximum length less than 5060 tokens, or word you can say. But those words, if broken down into the tokens, so those words can be broken into even more number of tokens. So if you see there a 50 word is limit in your data, then the number of tokens could be like 70 and 80. Sometimes it happens. For example, if we break down this tokenization, so this tokenization will not be considered as a single word or single token. This tokenization will be considered as 2 token. How? Because this token will be considered as a single token, and then this ization will be considered as another token. So this will be there a 2 token there. Alright, let's go ahead, write our some of the code here to understand that how this transformer does the tokenization. As you already know that to train our text classification or emotion classification model, you need to first tokenize your data. Thereafter, a token encoding will be done there, and then the token embedding will be generated along with the token positional embedding. Then these will be fed to the encoder stack, and thereafter a hidden state. So this hidden state is a contextual embedding state here. So the embedding will be generated as per the context of the word at this hidden state. So once embedding is generated, then it will pass data to your classification head. Generally in classification head, we put there a fully connected neural network or DNN layers there, and then final predictions will be done there. So I'm gonna import here auto tokenizer. So you see transformers here. Transformers have many methods to implement these tokenization techniques. So there is one method where it is known as auto tokenizer. So you can say here from transformers import auto tokenizer. So in this, what will happen, this auto tokenizer, if you give here auto tokenizer, so it will automatically fetch the tokenization technique which is used in your model. So you know, whatever the transformer model you are using in your algorithm, you have to make sure that you use the same tokenizer on which your model was earlier trained. So we are gonna use here DistilBERT base uncaged model. You can search that DistilBERT model here. Just a second, let me show you here. Alright, so you search here this DistilBERT base uncaged model. So this particular model we are going to download here. So in this model we have there whatever the tokenization is used in this model, we will be using that tokenization by calling auto tokenizer. Some of the details of this model is given here. Model have total 67 million parameters, and the weights of this model is stored as floating point 32 bit. That's mean the 4 byte for each of these weights are used there. You can also see some of the techniques to use this DistilBERT model directly. Like you can import DistilBERT model from here itself, like from transformers import DistilBERT tokenizer and then the DistilBERT model. And the difference what we are using here, we are using auto tokenizer. So if you pass the model name, this tokenizer will automatically make sure that it fetch the details of the DistilBERT tokenizer. So what's the use of doing this? So if you remember just the model name, you do not need to change anything in the import. You can just pass the model name from the variable itself and the tokenizer will be automatically fetched there. So I'm going to use here model CKPT, that's the model checkpoint, and that model I'm going to use here this model. The name of model is here DistilBERT base uncaged model. So uncaged says that here if you use capital letter or a small letter, those will be treated as a single case, or those tokens will be treated as a single token. So thereafter we are going to get here the tokenizer. Tokenizer is equal to auto tokenizer dot from pre-trained, and in this we are going to give here model checkpoint. Now this tokenizer will be loaded here in this tokenizer itself for DistilBERT base uncaged. Now we are going to give here a text data, and then we will see that how the tokenization will be done there. I write here I love machine learning. Thereafter I write here tokenization is awesome. Alright, let's go ahead and create our encoded text. So as I told you earlier that it will create their token embedding, but before that it will do their the tokenization, that's the token encoding. So it says that here tokenizer. So this is the tokenizer variable which we passed. Now inside this we are going to pass here text data. Thereafter we are going to print this encoded text here. You would be able to see that this tokenization will be broken down into multiple tokens. Now if you count these number of tokens, so how many tokens you would see here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So out of these 12 tokens, the first token and the last token, these two tokens are special tokens. Alright, so these two tokens are special token. The first one is known as CLS, This second one is known as separator token. So CLS says that from here a sentence is starting, and this one says that from here a sentence has ended there. Now other than that, we have here 10. So out of 10, if you count these as word tokenization, 1, 2, 3, 4, 5, 6, 7, and then 9 and 10, 7 and 9. So the one thing is missing. So how would you know exactly how this tokenization is done? Alright, so that for that purpose, you can use here convert these IDs into tokens. We will come back later to describe what are these IDs. Let me show you. So I write here tokens is equal to tokenizer dot convert IDs to tokens. Then I write here encoded text dot input IDs. So I'm going to pass these input IDs, then it will be printing us the tokens here. Now if you print these tokens, you would be able to see this, but let me just print it here so that I can see it in single row. So now, as I told you earlier, that this means CLS. Now one more thing, you see this capital letter got converted into small letter. As I told you earlier that we are using here DistilBERT based uncased model. That's mean whatever we do with the casing in our text data, those will be treated as small letter text data. Thereafter we have lab machine learning, and then we have here the two tokens for exclamation mark and then for here period. Thereafter this token got converted as a single token. In fact, these tokenization got broken into two tokens, token and ijson. So whenever these tokens are broken into multiple tokens, then you will be seeing there double hash there. So why it used this technique? Just to reduce the dictionary size. To reduce the dictionary size, this technique is used, because in tokenization, base word is here token, and then this ijson is here. Now you can see here with this, it will be having here token, only one token there, and this ijson can be used with the personalization as well, or any other tokens or any other word where this ijson follows there. So because of that techniques, your model have less number of weights and less parameters, because this dictionary is less there. Moreover, actually the parameter does not depends on the dictionary size, but overall to hold the large dictionary, it will take a less space. But if you talk about the actual model parameter where the model training happens, that does not depend here. Alright, so that's how you see. Now what are these numbers? As I told you that this is the dictionary. Alright, so these words are treated as a token, and for each of these tokens, these numbers are assigned there. So as large dictionary you have, those numbers will be assigned for your whole dictionary. So what is our dictionary? So our dictionary means here we have a very less number of parameters, just 10, there you count just 10 token. So actually for this text data, our dictionary size is just 10, but we are not talking about our data. We are talking about DistilBERT data, on which DistilBERT model was trained. DistilBERT model was trained on book corpus and Wikipedia data. So in that data, how many tokens it has in the dictionary, that you can check here with the token vocab size. So with this, you would be able to see here, it is having there 30,522 tokens. And what is the length of the tokens? What is the length of the model which can process the maximum number of tokens? So that you get it here, tokenizer dot model underscore max dot length, something like this. Now you will see here total 512 maximum number of tokens can be processed in one go. Alright, so this is how we do on sample data. Now let's go ahead do this on our actual data. So how we are going to do that? In fact, that I'll be doing here itself, and then I'm gonna just write here tokenization of the emotion data. Alright, let's go ahead and do the tokenization of emotion data. Now you have seen our emotion data here. So in this emotion data, what do you see here? If you remember earlier, we have actually set these emotion data as the format as the pandas data format. So that pandas data frame, we need to now reset that so that we can work on this whole data in one go. So I'm going to reset that format what we did earlier so that you can do with emotion.reset format. Now with this reset format, now you do not have this emotion as a pandas data frame. Now we need to do here a tokenization for our whole data. Let me again take you here just to explain how and what we are going to do here. You have seen on sample data how the tokenization is done. Now these embedding and token embedding, encoder, hidden state, all these we will be implementing with the BERT itself, with the BERT model. So we have imported just BERT tokenization. So BERT tokenization does not generate these embedding. BERT model generate these embedding. So I'll be also showing you some sample embeddings generated by the BERT model, and thereafter we will go and generate embedding for our whole data set. Let's go ahead and first you do here tokenization for our whole data. Now as you know here, this emotion have three split data: train, validation and test. Now we want to do this for all data, I mean all split. So for that we need to implement here a tokenization method. Along with that, I'll be using here a map function. Alright, let's go ahead and implement here the tokenization method. So I write here def tokenize. In this tokenize, I'm going to pass here a batch size. So this batch means we will be passing here data in the batches, and it will be doing the tokenization on those batches. As soon as I get the data, I write here tokenize. Okay, something like I need to write here some variable, maybe temp, let's say. Okay, so I write here tokenizer, what we had seen earlier, batch, in that the text data. Now you see there, whatever the batch we will pass here, it has their text data and the label. So we will be doing tokenization on the text column. Thereafter, I say here the padding equal to the true. So what happens here, we do not have all these sentences with the equal length. So the length of sentences are not equal, but machine learning algorithm need all those lengths equal. So in that case, what we are going to do here, we are going to do here the padding. For those data where length is not matching, we will be padding those data with 0. And then what happens if the length of word is, if the length of the sentence is larger? So in that case, we are also going to truncate there. So the truncation will happen. Thereafter, I'm just gonna return this temp here. Let's go ahead and check this. So I write here print tokenize, and in this I'm going to pass here our emotion data, and then we will be seeing how this is going to do. So I pass here first two data. If you check this will pass first two rows including text and the label. Since we are reading here just text, it will do the tokenization on just text data. If you just run this, alright, some error is coming here. It says that, okay, this is not text actually. We need to pass here train split. Okay, so now you can see here clearly our first sentence was actually a very small sentence. That is why all other are the padding is done here, and you will see there this CLS does not change. So this indicates that your model do not need to look after these token. That's the CLS token. Similarly, you can see here in the attention mask. So this attention mask is again telling us that how many tokens your model need to see and how many tokens your model need to ignore. So your model need to ignore for these tokens for the first sentence. If we check it just for one sentence, you will see here. Alright. So we are doing here just two tokenization. We are doing here just one tokenization. So for one tokenization, maximum length would be exactly the same length of the first sentence. But as soon as we pass here the 2, so now the maximum length, your second token is having the maximum length. That is why you are not seeing anything 0 in that one. But if you pass even more here, probably you would also see here 0 in, okay, there is no 0 in second tokens, but the zeros are padded there in other consecutive tokens there. Alright, that's how you can do the tokenization. Now once tokenization is done, thereafter you need to create here encoding for all the splits here. So that I'm gonna do here emotions encoded is equal to emotions.map, and then I pass here tokenize batched is equal to true, and then I write here batch size is equal to none. Alright, so with this what happened here, emotions, okay, seems like this should be emotion only. So here we have emotion.map tokenize. That means we are passing this method in the map function, and then it says that batch is true and batch size is none. That means at one go it will pass train split as a whole data, and then test split as whole data, and then validation split as a whole data. That's how these emotions encoding is done. Once you have done your emotions encoding, let's go ahead and see the total column names available in this emotions encoding. Now if you print this emotions encoding, you will be seeing here 2 more columns. So this is what we were having here, input IDs and the attention mask. Now these 2 additional columns are added in each of our splits here, input IDs and attention mask. Now we would be able to pass this whole data to generate the embedding for our model. Alright, let's go ahead and build a sample model to understand that how these embeddings will be generated. So I'm gonna create here first text data. I write here again, I think we already have our text data where we wrote I love machine learning tokenization is awesome. Now I'm gonna create here inputs, or you can say the encoded inputs equal to tokenizer, and in that I pass here text data and then return tensor is equal to pt. So this one is needed to do because it will return tensor as PyTorch tensor so that we can train our model. But overall you would not see any difference here. It will be exactly the same like we see there. Okay, something is wrong. Okay, wait a second, let me see it here. Okay, it is saying that this has got unexpected return tensor. Just a second, let me see it. I think I have made here a typo. It's return tensors. Alright. So you will be getting here PyTorch tensor, although you would not see any difference here in input output. It's the same like we used to see here, but only the difference here it is created as tensor here. So we have our text data, I love machine learning, tokenization is awesome. Let's go ahead and build the model and then we will generate embedding for each of these tokens. So I write here from transformers import auto model. Alright, so why do we need now auto model? Earlier we imported auto tokenizer, now we are importing auto model. Otherwise we can simply import here DistilBERT model itself. Again, the use of this is you can just simply change the name of the model checkpoint, and then you can load any kind of the model if you use auto model. So I write here import torch and then model is equal to auto model, and inside this I write here from pre-trained, I write here model checkpoint, model CKPT, that's the model checkpoint. Once you have your model, you can print your model here itself, and before that you will see here it will download your model, so it's gonna take some time. Now it has downloaded model. Let's go ahead and check it. Now you have this DistilBERT model. Now it has these layers there inside that, because as you saw earlier that the first few layers will generate embeddings there. Thereafter a transformer, which is their encoder stacks are used there with the multi-head self-attention technique. Those will be used there to generate the final output. And there you have output norm, that's the output layer output. Alright, that's the model. Let's go ahead and train this model. Since we do not want to train our model, in fact, we want here to generate embedding, not the training. Okay, so let's go ahead and generate the embedding from our model. So if you just want to generate embedding from your model, then you do not want your model to adjust with the gradients when you load your model. So for that purpose, I write here with torch.noGrad, that's mean no gradient, do not load gradient. So this will make it faster model. Thereafter I write here outputs is equal to model, and then I write here double star, and then I write here inputs. So what happened here, we have our input, you see there tensor for input IDs and attention mask. Thereafter we pass these to model, and then this is generated as output here. Thereafter I write here last hidden states equal to outputs dot last hidden state. So what do you see here? You have outputs, that is this one, that's the model output. The model output will be having all of these layers, but we want last hidden state, that's the last state. This state we want, if you see our this one, so you will see there this hidden state is the last hidden state. So that we want, we just run it. Now we can see that it is stored there in last hidden state. If you want to inspect it more, you can simply write here outputs here. You would see there it will be having here base model output as last hidden state. And here it has these embeddings generated. Now if you print this last hidden states, you will get those embedding. And if you check the shape of these embedding, you will get here the total number of tokens, 768. So this is vector length generated by DistilBERT, and this is the total number of tokens present in your data. Do remember here, this is also generating tokens for your CLS and separator, which is the special tokens there. Alright, so that's how it generates the embedding. Now once you have those embedding, you can use your classification head model to do a classification on your data. Now I think the concept is super clear to you. You need to first tokenize your data. Thereafter you need to generate embedding, and then you need to put here classification head in your model, and then you do the prediction here. So now here the two techniques with which you can do the predictions or the fine tuning. So the one technique is you can attach this classification head directly into your model hidden state, and then you can retrain your model based on whatever the errors are coming here after the classification head. That's the one technique, which is the correct technique, and the and will produce more accuracy. Another technique, you have got your vectors here. Once you have got your last hidden states vector, you can simply use any kind of machine learning algorithm to do the classification on this vector itself. Like you can use the logistic regression, SVM, or any kind of deep learning algorithm, CNN, RNN, or whatever the algorithm you want, you can use on these vectors itself. But the problem with these vectors, but let me tell you first the benefit. Benefit is that this is fast. You do not need to train your model. You do not need to retrain your model. So it is fast here. But the problem is, if you do not retrain your model, then sometimes you may not get the correct context. So if you use second technique where you do not retrain your model, it is faster but produce less accuracy. First method, where you need to do the training, produces high accuracy but takes a little bit more time. Alright, so we are going to follow here the first technique, in which we will be fine-tuning our transformer model. So as you see there, in fine-tuning, we will be attaching this classification head to our hidden state there. Now, other than that, we also need to import here auto model for sequence classification. Now you can see here, this DistilBERT tokenizer is imported from there, and then the TensorFlow DistilBERT tokenization model is there, and here is the PyTorch DistilBERT model is here. Alright, so but these models you cannot use directly for the classification. These models are trained for some other purposes, like masked language predictions, or you can say the token predictions. These models are trained generally on the token predictions, or filling the mask values, something like here. So the goal of life is, and if you just run it, now you will see there the happiness, it says that the survivor salvations. So this is kind of the mask language, and if you change this mask, let's say to happiness, and if you just delete this age, now you will see this mask will be predicted with this mask will be predicted there. So it will take a while to load the model. Now it says that age is perfectly fitting here. It's the probability is quite high. The goal of life, age, happiness. Alright. So whenever you have any word where it has some missing context, you can use these, although so that's not our current scope to understand where you can use the DistilBERT. We are already using DistilBERT for our emotion classification. So this particular method is going to help us to load our model for sequence classification, and it will also allow us to add these additional overhead to our model. Let's go ahead and import it. So I'm going to write here from transformers import. I'm just going to copy this thing from here itself. Import auto model for sequence classification. Alright, once you have this, thereafter, how many number of labels you have here? As you know that we have our classes stored in classes, so you can simply take the length of the classes. Thereafter, we need to also find out if we are using CUDA or a CPU. So with that, you can run here torch.device, and thereafter we are going to use here CUDA. If torch.CUDA.age available is CPU. So what it will do here, it will check if GPU is available in my machine. It will use GPU for the training the model. Otherwise, it will use CPU here. Let's go ahead and create a model. So I write here model, auto model for, auto model for, in fact, let me copy this whole thing from here. It is quite large. Auto model for sequence classification dot from pre-trained, and then I write here model CKPT, that's the model checkpoint. Let's go ahead and run this. Now once you run this, it will tell you some weights of DistilBERT were not initialized from the model checkpoint. This happens because some weights are initialized randomly, so it's okay, perfectly fine the first time if you load your model. The few things we are missing here, number of labels we are missing. So how many labels we want here? We want here total number of labels is equal to number of labels. Thereafter we want to load our model to the device. So to the device, that's mean either load our model to CUDA or CPU, wherever if CUDA is available. So it will load this model there. But how would you check that if CUDA is available? You can simply print this device here. If I just print this device, you will see here a CPU there. Why CPU? Because I have not connected my notebook with the GPU yet. You may ask why I did not connect this. Since this is quite large lecture and keeping my GPU attached with this Google notebook, it will ultimately expire my credits. So unless I need to train our model, unless we need to train our model or you need to train your model, I would suggest you do not connect your GPU. Otherwise, it will consume your credits. So after some time, Google will say that you have consumed your credits, free credits in fact it is. So free credits, if it is consumed, then you may need to wait few hours to get it again. So that's why I did not connect with GPU. Although during the training, I'll connect it with the GPU. Alright, so once you have got all these stuffs, now we are ready to build our model. Alright, let's go ahead and build our model. So I write here from transformers import training arguments. So with this, what happens here, from transformers import training arguments. Now we need to build our model. So I write here batch size is equal to 64 and then model name equal to, we already know that in fact, okay, but this is the model name which will be stored in our local computer. So there I'm gonna give here DistilBERT fine-tuned emotion. This is our model. So let's go ahead and create training argument. Thereafter we will pass this to the trainer so that the training can be done. Now I write here training args, that's the training argument, is equal to training arguments, and in this I pass here first of all output dir. So what is this output dir? This is directory where our model will be stored as the model name, whatever I give here. That means it will be stored here in current directory. It will be stored here after running the model, after training the model. And number of training epochs we are going to give here is 2. Thereafter learning rate here, I give here 2 into 10 power minus 5. That's the learning rate which we are passing to our current model. Thereafter I pass here per device train batch size. Okay, that I don't think we need to pass anyway. You check here, the per device evaluation batch size is 8 and these are default batch size. I think we can change these as well. So I write here per device eval batch size equal to batch size what we have assigned there, and similarly we can say here per device train batch size equal to batch size. something like this. Thereafter, once you have given this, then I pass here weight underscore dk equal to 0.01. That's how the training will happen here. There would be a little weight dk there. Once you have done this, thereafter you can simply write here evaluation strategy. I'm going to write here epoch. Thereafter disable tqdm equal to false. That's mean whatever the progress bar, if you make it true, those progress bar will be disabled here. Okay, let me again take you through from here itself. So first it says that you have output directory, model name, number of training epochs, and thereafter you have here learning rate, and then you get here the per device evaluation batch size. Thereafter you have this one, so I'm going to put it here before that, so it's a little bit more convenient to do here. So we have per device train batch size equal to the batch size, then we have per device eval batch size. Okay, somehow this error is coming. Let me just remove that error. Then again I'm just gonna copy and paste it here. Batch size. Okay, this batch size is also wrong here. This is the batch size, and here per device, you check here this train, it would be here eval. That's the evaluation. Okay, then weight decay, all these are here. So weight decay, that is how the weight will decay while pre-training, while actually the retraining. Evaluation strategy on epoch. On every epoch, evaluation will be done. That's mean the accuracy metrics will be calculated. Alright, let's go ahead and run this. As I run this, it says that invalid syntax. Perhaps somewhere I might have forgot the comma. Okay, here. Okay, so it says that we have got here something. Okay, here it's actually wrong here. It should be here strategy. Still something is missing. Okay, all right. So this error is coming here, and the solution is we install here accelerator and upgrade our transformers. But anyway, currently we are using this on a CPU machine. Now this is the time when we can switch our machine. Now we are going to switch our machine to a GPU machine. Just a second. Not this one. Okay, so somehow it's not able to connect it properly. So I'm just gonna make a guess here. T4 GPU machine, it's gonna connect here. I just click on OK. So it's again here connecting. Let me just zoom it a little so that we can see it properly. Now a new GPU is connected. T4 GPU is assigned here, and it's a free version of Google Colab. We have total system RAM 12 GB and disk space is here, and the GPU space would be around the 12 GB as well. Alright, now I need to run everything from the starting. So how you can do that? You can simply come here, runtime, and then you can say here run all. So it's going to run everything from the starting. Alright, so the first it will install these necessary packages here, and then it will move ahead. Alright, so this is the one-time process. It's gonna take some time, and then I'm gonna just stick to our code where we had our training argument here. Alright, so we'll wait some time, let it finish here, and then we will continue. Okay, so seems like a same error we are getting again. Now we need to just run this. So I run here pip install transformer torch and all these. I'm just gonna do it again here, and thereafter I need to just do this accelerate from here itself. So like it is suggested here, seems like we need to do all those again here. Let's go ahead and run this. Okay, let's go ahead and run this now. Okay. Now I need to upgrade our accelerate and transformers both from the starting itself. So I'm just gonna copy that from here and then I'm gonna paste that in the starting itself. Here we had. So I write here pip install upgrade transformers, and thereafter I write here pip install upgrade accelerator, this one. So all these are installed. This data set we will also install as upgraded version, and these two libraries anyway we do not need. Or what we can do, we can keep these but with the upgraded version. The latest version will be installed. Now once all these things are done, then we can restart and run all these together. So it will upgrade our transformers, accelerator, dataset, vertwidge and UMAP learn library. So it may take a while to finish it. Let's go ahead and wait for some time so that it can finish these initial training part. Now you can see here the training argument is already done here. Alright, so we needed to upgrade our transformers and also accelerate. Alright, so we were also discussing about compute metrics. That's mean how evaluation will be done. Evaluation will be done after each epoch, and we will be using here accuracy and F1 score to calculate our accuracy and evaluation metrics. So for that you need to import from sklearn.metrics import accuracy score. Thereafter you need here F1 score. Thereafter you write here def, that's the define compute metrics. Then you write here pred. Alright, thereafter you write here labels is equal to pred label IDs. Thereafter you write here preds is equal to, you have here labels equal to pred dot label IDs, then you have preds equal to pred. So but before that let me explain you what we are doing here. This is compute metrics. It takes here the predicted values. So in predicted values you will be having their label IDs considered as 0 to 5. That's the label here. Thereafter you do the prediction here. So I write here pred dot predictions dot arg max -1. That's mean get the argument prediction argument. Thereafter we are going to calculate here F1 score. So I write here F1 is equal to F1 score, and then I write here labels preds. Thereafter I write here average weighted. So this is the F1 score. F1 score labels preds average equal to weighted. Thereafter you write here accuracy then you write here accuracy score, and then you write here labels, and then there is spreads. Alright, so F1 equal to the F1 score, label, spreads, average, weighted. Now you have got here accuracy score, labels, and prediction. So this one is actual labels. So after each epoch, evaluation will be done where actual labels and the predicted label will be passed, and based on that these accuracy will be predicted. Thereafter I write here return accuracy and then also we return here F1 score, we return it as F1, something like this. So we have now our compute metrics. We are ready to do our model training. So I write here from transformers import trainer. So this trainer will be used to training, and this training argument will be used to pass these argument in our trainer. Thereafter I write here trainer is equal to trainer. Inside this I pass here model equal to model, which we had created earlier. If you remember, there we had our model, that's the model equal to model. Thereafter we are going to pass here arguments. So the arguments are here training args, that's the training arguments. Then we pass here compute metrics, and the name of that is itself compute metrics, that the function which we just made that function, that's the compute metrics here. Alright, so we have here model argument, training argument, and then we have here compute metrics, that is stored as here again a compute matrix. Let me just write those as like this. Thereafter, yeah, this one in fact we are doing copy and paste it here. Thereafter I write here train data set is equal to emotion encoded. Do you remember that in the train data set we had emotion encoded? Inside that we had here train split. Thereafter we have here eval data set is equal to emotions underscore encoded validation data set. Thereafter we need to also pass here tokenizer. The name of the tokenizer is itself tokenizer. Now you see what happens here. We have model, training argument, compute matrix which will be calculated here, training argument, train data set which is emotion encoded. In this encoded, if you remember, we had encoded IDs. Thereafter we had here eval dataset, emotions encoded validation dataset. Again here encoded token IDs and attention mask is there, and then we are also passing here tokenizer. Let's go ahead and run this. Thereafter you can simply run here trainer.train. That's all you need to do here. You just run this. Now your training will start here. You might need to wait for a while. Let your training finish here. It's gonna take some time. Once training is finished, then we will start again. Okay, this error we we got here seems like some problem is here with our compute metrics. It's here. It should be pred.predictions.org max. Let's go ahead and run that one and then this one. we need to wait for a while so that it can finish its training. Alright, so the training is done here. Now you can see your training loss, we have 0.177, validation loss 0.15. So loss is still lesser than the training loss, and you see accuracy of your validation model is 93.5%. If you remember earlier when we were starting this tutorial, I told you that even though we are having imbalanced data set, but transformers are good to work with the imbalanced data set. If you apply traditional algorithms like SVM and XGBoost, all these algorithms, or TF-IDF, you may not get a better accuracy than this one. So transformer really works better. Now we have trained our model, we have got our evaluation accuracy. This is time to do some testing on our model. Let's go ahead and do first our test accuracy. So I write here preds underscore outputs equal to trainer dot predict, and then I pass here emotions encoded test data. Thereafter I write here preds underscore outputs dot metrics. So this is going to the prediction on the test data. It will tell us that how much accuracy we got on test data. So on test data we got accuracy 92.7, on validation data we had 93.5%. So it's a little less on the test data, but overall it is really very good accuracy, which you can use where you can use your model in production. Let's go ahead and plot a confusion matrix just to understand that where this particular thing is going wrong. Alright, so wherever we are getting around 7.5% less accuracy, we just need to know that which classes are creating problem here. So I write here import numpy as np. Thereafter I write here y underscore preds equal to np dot argmax. That's when we are going to get the maximum argument from the preds output dot predictions, and then we say here axis equal to 1, and then we have here y true as well. So in y true we have here emotions underscore encoded, and then inside this we have here our test column. Thereafter we are going to take all these rows, and out of those rows we are going to import here label. That's how we do it here. It says that the pred output is not there. Let me just copy that from there and then we put it here. So we got here y pred and y true. Thereafter we need to print here classification report. So I write from sklearn dot metrics import classification report. Then I print here the classes, which classes we have. Thereafter I print here classification report. In this classification report I pass here y true and then y pred. I'm sure if you are studying here transformers, I'm sure you know all these things better, like how classification reports work and what is the confusion matrix. So in this you can clearly see this one where we have surprise. Seems like surprise performance is a little less here. Alright, other than that we see sadness performance is quite good, and if you compare this with the value counts, if you remember we had our value counts, it was perhaps this value counts. Okay, it wasn't this one. Anyway, we had there somewhere this value count. Let me get it here. It's label counts. Let me just print that label counts there just to understand that what type of labels we have here, that's the label counts. In this label count, we see here sadness has large number of tokens, large number of actually the rows. So this accuracy is quite good. Whereas we had for surprise, we had just 572. That's why we see here a little less accuracy. So as you put more and more data, your model will start performing better and better. Alright, so during the training, our model has already stored its data here in DistilBERT fine-tuned emotion. The name was given here itself. Now you see DistilBERT fine-tuned emotion. Now you can download this data. You need to zip this data first. You can zip this model and thereafter you can download this model. You will get here option to download. Alright, you do not need to download all these one by one. And here it has the checkpoints, and here it has the total number of runs we run it today, and here these outputs you can see. Alright, so after zipping this, use the command to zip this model, then you can download and then you can use this model for the testing. Now let me finally show you how you can do the prediction on your own data set. So let's say I have our data set where we have text data. On this text data, we want to do the prediction. So it's very much simple. You need to just write here. Okay, I'm just gonna write this whole thing from here to here. Just make sure that you see this, what is written here. Then I write here input encoded equal to tokenizer this text data, then return tensors equal to pt. Then we want this to our device on which our model is currently stored. Thereafter we just need to do here prediction. So I write here with torch dot no grad. That's mean you do not need to calculate gradients. Then I need to write here outputs equal to model, and then we pass our inputs here. That's all you need to do here. You have your output. Okay, it seems like all tensors should be on same device. We have this on device. This model also need to be on device. Let me just write that. Model is equal to model dot to device. Alright. Seems like something is wrong, or we don't need to use this thing actually. Probably. Let me just see it here. Okay, still we are getting this error. This error we shouldn't be getting. Okay, okay, problem is here actually. To device, and this input encoded need to become here. Alright, that's how you need to do this. If you just run this, then you check this output, what you will get here. This output will be having here logits. So these logits are actually the predictions. So what I write here logits is equal to outputs dot logits. Thereafter I do here prediction. So I write here pred equal to torch dot argument max from this logits, and then I say here dimension is 1, and then I say here item. Now if you print this pred, what output you will get? So you will be getting here 1, but we do not know what is 1. So you can simply print it with the classes and pred. Now you would be able to see exactly the name of your class. It says that joy. Now let me change this. Again I say here I love you. Now this is love. But if I write here I want to die, then it says that sadness. If I say I want to kill you, then probably it would be anger here. So that's how you do the prediction once you have your model. Now you can zip this model and then you can download, you can load this model, and then you can use further this model. If you do not know how to load this model, you can reach out to me by commenting on the video link on this video, and then I'll tell you how you can load that model. Alright, this is all about in this lesson. Thanks a lot for watching this. Please do subscribe this channel and share this video with your friends and social media. Thanks a lot. Bye bye. Take care.